That's how he told me 25 minutes. He already knows that I go overtime all the time. So he's like, no, seriously, 25 minutes. So I'm here to talk today about how we can use priors in testing. When I go to people and I start talking about, hey, I'm a Bayesian, I think you should use Bayesian methods in testing, one of the things that always comes up is, well, how do I develop that prior? And a lot of times they go, well, I don't have the right subject matter expert, and I don't have the right data, and I don't know how to do this. And so I wanted to take some time to talk about how do we think about priors. And so when I think about a framework for priors, I'm really thinking about how do you ask the right questions, and how do you think about the right type of prior to do your analysis? Because we could have as many priors as there are people in this room. So how do we come to a conclusion as we go into testing when we have a test team that has, multiple different people in there with multiple different agendas and multiple different experiences? So we'll talk about Bayesian methods in test and evaluation. We'll talk about the informativeness of priors, some of the types of priors that I think could be useful for test and evaluation, an example of how priors can be used across the continuum of testing, and then some updates, how that prior updates across testing, and some key takeaways. So Bayesian methods really come down to combining previous information with current information and updating our beliefs about a specific event in question. And so as I think about what Bayesian methods do for testing is we as testers come to an event and we have some sort of understanding of the system, and that might be from previous testing or personal experience, and we need to also be able to answer questions that the decision makers need to know about how that system performs. And so as we go across testing and we think about this entire continuum, it really is, in some ways, the epitome of a Bayesian framework. I continually learn information about a system, and I continually update my understanding about that system. And that's what Bayesian methods do, is we take that understanding and we quantify it into analysis. So there are a few ways that I think that Bayesian methods can help make a more efficient and effective test, and they're all listed on the screen here. And so one of the things is I really think that it's a great way to naturally leverage that previous information. So we heard this morning a lot about being data-centric and getting this data and using the right data, and then how do we use that data appropriately? And so thinking about Bayesian methods are a really great way to look at that previous data and leverage it in our current testing. And slides are going for me. So I guess I better move on to this one, which is really just to say we've all heard about the OODA Loop. Everyone has learned about that in various trainings, and when I think about the Bayesian method, it really is the statistical manifestation of the OODA Loop. And so it's a very natural way of thinking for most people, and so I think that it really leverages how do we make decisions and not ready to go on. How do we make decisions, and how do we talk to the decision maker about what statistics means? And so with that, we'll be focusing a lot about priors today, where how do we continually update this information to make good decisions about system performance? So with that, we're going to talk about what priors actually are. So priors are a way to reflect our beliefs about the current state prior to testing. And so what do we think we know about model parameters coming into a test? Especially if we're later in testing, we probably know something about how altitude is going to affect the aircraft if they're trying to employ a weapon system. These kind of key features of information can be incorporated into our analysis to give us a better understanding of system performance before we go into test that we can then update to get better information on the outside of test. We can reduce the uncertainty we have in system performance through the use of these priors, combining that with our current information. And priors are going to be selected before we see the data. These are going to represent this continual idea of updating our beliefs. When we talk about the informativeness of priors, there are really 4 types of priors that we think about. These are classes of priors, if you will. And this is what we're focusing on in the beginning of this discussion. So the first one is called a non-informative prior. This is a class of priors that try to be, as the name would suggest, non-informative. Then we're going to talk about weakly informative priors and move on to one of my favorites, which is informative priors. And then degenerate priors we won't talk about today, but if you're looking at something like an ANOVA model where you have constraints to your model, those are going to be something that can handle your constraints. So with that, Let's start with non-informative priors. You also might have heard of these as reference priors or convenience priors or vague priors. They come by a lot of different names. And what non-informative priors are trying to do is they're trying to incorporate no information about the system or about the model parameters into our analysis. We're trying to allow the data to drive the decision from a Bayesian perspective. And so with that, we have that our reference priors or our non-informative priors are easily overwhelmed by our data. So this is a really great way to start thinking about sensitivity analysis. Sometimes we can mimic the frequentist approaches to analysis by using these types of priors, and they tend to be very convenient for use in the mathematical computations. So those are the benefits, but they have some limitations that you need to be aware of when you think about reference priors. And if you've been to some of the presentations, both here and in other places, a lot of times people will say, hey, I'm doing Bayesian methods. I'm going to use non-informative priors in my analysis. But there are some limitations to using those priors. And that is that it's never possible to include no information into an analysis. Even our non-informative priors, that's why I have that in quote, tell us something. They can also put a majority of the probability in weird places. They might not result in a proper posterior distribution, and they can be computationally inefficient. Now, in testing, when we think about we need to do analysis on a quick turn basis, especially if we're thinking about interim analysis, we want to have computationally efficient priors. With that, we can think about weakly informative priors. And weakly informative priors are going to be priors that take on the natural bounds of a parameter. So if we think about, say, I am trying to procure the next street legal car, and one of the things I want to know about that car is what is the max speed it can go? Well, if you look online, right now, the max speed of any street legal car is about 330 miles per hour. And with that, if I'm thinking about, they really want me to go to informative priors. With that, I can think about developing a weakly informative prior that says if I know the current technology is going to keep me at about 330 miles per hour, then I'm going to be able to create a prior that says, okay, I want to incorporate 330, but I'm not going to incorporate values that go up to, say, like 600 miles per hour because the technology we have today, it's just unreasonable to be doing that. So instead, we can create weakly informative priors that say these are the bounds that our model parameters can take on. They're going to be useful when it may be complicated to get really good informative priors, and they're going to be useful for creating and eliciting functions appropriately. You're fine. Thank you. So with that, we can use these weakly informative priors to start giving us some of the benefit of informative priors while still remaining diffuse about the limitations to what we know. The limitation of these types of priors is that we are intentionally being weaker than the current information that we have available. And when we do that, we aren't getting as much benefit from our priors as if we use all of the information available. So, informative priors. Informative priors are attempting to model all of the information that we have available. And that can come from subject matter expert opinion, summary statistics, raw data. There's a lot of ways that we can incorporate that information. One of the limitations of using informative priors, which is going to be the focus of this talk, is that it requires thought. And it's hard to do. It's hard to get information about model parameters from subject matter experts or from data. But the benefit that we get from using these good informative priors, which is namely that we can have smaller fitted values around, smaller standard deviations around our fitted values, generally outweigh the cost of spending the time developing good prior information. And we as testers are already talking a lot about the system before we go into test. We're talking about what factor levels are important. We're talking about how that's going to affect the response or the outcome that we expect. And we're already getting this information, we're just not quantifying it in our analysis. And so by taking on a Bayesian approach, we're incorporating all of the information that we as a community know about the system into the analysis. They also help with computational efficiency. So, I'm going to give a simulated example for you to think about as I talk about what types of priors might be useful. And so we're going to think about procuring a new computer. So say you're some technology company that is interested in procuring this high-performance computer, and you want to know about the number of defects that you're going to have in these computers, and you want it to be below some proportion of 0.1. So we have this distribution of data. We're going to say whether there's a defect or not. So we'll allow the data to be a binomial distribution with some proportion theta, and theta with the brackets on it is going to suggest that we might have factor levels that influence theta. So generally speaking, we have this computer. It has potentially some bugs. We test it under factor levels and conditions, and we want to make an assessment about theta, which tells me about the proportion of my computers that have this software defect. So as we go into testing, if we're under this construct, we're going to start thinking about what can we know about theta, or potentially the factor levels that make up theta. And so we might think about, do we have previous data? If we have previous data, then we have to start thinking about, well, what is that data? Is that data similar to the data I'm going to be collecting in my next phase of testing? I'll refer to that as exchangeable. For those of you who aren't familiar with the term, you can think about that as like IID. Is my data the same as what I'm going to see going into my next phase, or is it not? Is it different in some way? I'll refer to that as non-exchangeable. Is it raw data? Is it summary statistics? Is it potentially previous data from legacy systems? So if you're upgrading a system, is there some information there? And when we think about those type of information, some things I've noticed from test teams is they go, oh, well, it's a different system, that we can't use that information in our prior. But we have ways that we can think about building priors that can actually leverage this type of information. We can then ask ourselves, well, do I know the natural bounds for the values that we expect to see during our testing to go to the weakly informative prior? Do I have subject matter expert opinion if I don't have data? Or do I need to represent no information because the system is so new and I have so little understanding about the system that I can't create some sort of informative prior? Today, we're going to focus on what happens when I have previous raw data and it's not the same, or it is the same relative to the system we're using today. So the first scenario I'd like you to consider is a very baseline scenario. This is going to be like the ideal case of thinking about how priors get updated. And the scenario would be, say you're under integrated testing and you've tested under specific factors and levels for the computer example. Then you transition to operational testing and you're testing under the same exact factor levels. And this might be because you didn't get enough information in integrated testing. For whatever reason, there's no system change, there's no hardware or software change. It's literally the exact same test. Under this example, we would consider this data exchangeable. We would consider it IID. And so in this case, how we would approach that from a Bayesian perspective is we would take the posterior distribution from the integrated test, and that would become the prior for our current test. The prior for the operational test, having been that posterior, would then be incorporated, and our posterior would be based on both what we saw in the operational test as well as what we saw in the integrated test and the prior that we used in the integrated test. This is a traditional approach that Bayesians use when that data has the similarities of exchangeability or similar to IID. However, as we know in this room, most of the time this is not the case that we're operating under any testing event. We see changes. The whole point of going through our continuum of testing is that the system changes, the system updates, we test under different factors. So, before we get there, I have pictures for you. So how that looks visually is if you went to the integrated test, and this is your posterior distribution, then now you go into your operational test and you collect your data, and you combine the operational test data from the likelihood function with the posterior from your previous test, and that's going to create your posterior distribution for your current test. And as you notice, because the prior information and the current information are very commensurate, the purple there, which is your posterior distribution, is tighter than if you had just done the likelihood function, which is the dashed line. That's the current data that you collected from your test. And so relative to a frequentist approach, which would look at the dashed line, we can get better standard deviation estimates around our fitted value, which directly translates to we know more about theta because we've used this good previous information. So now let's consider a similar test is retested under the same conditions. So a similar test meaning that between integrated testing and operational testing, something changed in the system. And now we have to think, is this data exchangeable or not? Is it the same or not? Well, if I just change the hardware, and that isn't going to change how the software works, then I'm probably back in scenario 1, where to answer that specific question, I can still use the previous data for that question, because it all comes down to what is the parameter I'm trying to estimate. If there's a software update that makes the software more effective and it's in a related task, say the bug happened when I opened Jump, and the software update I did was I opened programs faster, well, that's not fixing the bug, but it's related to that. That might be slightly different data that we need to account for. And then, of course, we could have a change where the actual bug was detected and fixed, and we'll talk about that a little later. So if we have that similar system that is tested under those same conditions again, but has had some difference to it, we can talk about using normalized power priors. So instead of just taking the posterior distribution from your previous test and using it as your prior, you can use what's referred to as a normalized power prior. And what that does is it essentially looks at the difference between your historical data that you had from your test that you would like to incorporate into your analysis through the prior distribution, and says, how similar is that previous data relative to my current data? And if those data start looking commensurate, then you want to use much of that information as possible. So say you updated the system to open the software faster, and that didn't have any effects on the bug, and so you're seeing the data is distributed the same way. You want to use as much information that you previously had to be able to talk about the proportion of software defects. That's what the normalized power prior allows you to do. And then if it's for some reason says, oh no, by opening these apps faster, I actually did affect the rate of the proportion of things that have a bug, it's going to minimize the use of that, because now that information is different. And so that's what the graph on the right-hand side of the slide is looking at, is as I use no information, I'm this flat line, which basically transfers to like some sort of reference prior using in your distribution or in your posterior. And then if you let A not be 1, then you see this peak distribution. That's back to scenario 1. I'm using all that previous information in my analysis. And if you're in between, it's a down-weighted information bringing into your current analysis. So this allows your previous data and your current data to decide how similar they are to use in your analysis. That's not something we as analysts have to decide. We can allow our data to represent how much information we should be incorporating into our analysis from the previous test via this power prior. And there's an R package that does this for you, which is really nice. Now let's say we're looking at a similar system that is tested under additional conditions. So if you were integrated testing and you were under specific factor levels and you went to operational testing and now you're looking at more factor levels, how do you handle something like that? Well, if there was no changes, then we would think, well, maybe scenario 1 might work. But we need to adjust scenario 1 because scenario 1 said that all our factor levels were the same. Similarly, if we made a software update that was something related, and so we get slightly different data, well, we might think we're back in scenario 2B, but it needs to be updated to account for those additional factor levels. And then we could also have the same situation where it's a completely changed system that affects our measure. How do we handle all of those? Well, if we're in the same system, then we can think about putting a prior on the things we already know about from the previous testing, and then use some sort of reference prior on the pieces of information that we haven't received before. And so that gets us this idea of a partial borrowing prior that says I'm going to put informative priors on the things that I know about already, and then the things I don't know about, I'm going to let that be maybe a reference prior or driven by a subject matter expert opinion. With that, if we then say, okay, I have similar data, but not the exact same data, we can do the same thing. So this is scenario B that's just extended to put the informative prior, depending on the prior you're choosing, in this case, the power prior, on the information that you know already, and put different priors on the things that you haven't seen in testing. And then what happens when we change drastically? The system has completely changed relative to this measure, because everything is relative to the answer we're trying to get. Well, then I need to start asking questions about how drastic that change was. Is it so drastic that I'm not in scenario 2 anymore? Is it so drastic that now I need to consider potentially not the raw data, but summary statistics and make that more diffuse than I expect it to be based on what I've previously seen? Do I need to have a subject matter expert come in and tell me the mechanism that changes to understand how my factor levels are affected, and can I model that? Or do I need to completely scrap the priors that I have and start over? And that gives kind of this idea of this continuum of testing. So when we start testing, early in developmental testing, we might not know a lot about the system yet. Maybe that's because we didn't get the information from contractor testing. Maybe it's because we're starting from scratch. Whatever the case may be, we might start with these non-informative or reference priors, vague priors that try to not say too much about the system. And as we go through testing, we can get more and more informative because we're looking at the same type of testing under the same similar level of variability, I'll say. And so we can start using more and more of the information to get better and better estimates for our model parameters. Then maybe we change to integrated testing. And now I've added more variability into my testing than I saw before. So now maybe instead of that informative prior that I just ended with, I need to go back to doing a more weakly informative prior. I need to add in more variability to account for the variability I didn't account for before. And then as I go into operational testing, I might have to do that. And so what this is just trying to demonstrate is that priors flow with how much information you have, how much you trust that information relative to your current testing, and how that changes as you go through different phases. You might have a system that is performing very well and doesn't change how it operates between different phases of testing. Then maybe you can keep that informative prior all the way through. Or maybe the variability is affecting your system so much that you have to revert back to priors that don't capture as much information. And so this is trying to demonstrate that priors, you think about them every time you use them. It's not you start with one and it just carries through the entire test. So with that, we've talked about naturally leveraging the previous information, even if that information is potentially dissimilar. And there are several types of priors that can be selected depending on what you're trying to accomplish with your testing. And they can be used across the continuum of testing. They're very flexible and they can change depending on what you're trying to accomplish. With that, are there any questions?
Hello, I'm Logan Osman, and I'm with IDA, and I found that quite interesting because I do a lot of testing with software. So,
Thank you.
I guess the question I have is, can you know a priori with any of your scenarios, unless I have no hardware changes, no software changes, no change to the conditions, whether or not I can use a weakly informative prior, or what prior I can use?
So it's kind of like some method for deciding how informative your prior should be based on what you've seen already?
Yeah, or am I really always in that last flow chart you had?
Yeah, so I think that when you think about your priors, a lot of it comes down to how comfortable the test team feels with the information they've already obtained and where they're going. And so if you are going from something like controlled testing to uncontrolled testing, you're probably not trusting that information as much. You're probably thinking about a more weakly informative prior relative to what you've done before. But I think it's very dependent on what the system is and how comfortable the test team is. Even if you go from a controlled environment to an uncontrolled environment, if there's a physical mechanism that you know is going to be affected in a certain way, you could possibly keep that prior distribution as informative as you want because you understand how that system is supposed to react. But I don't know that there's any cut and dry way to think about, okay, at this point, we need this type of prior. I think it takes a lot of conversation about how comfortable the test team is with the information they know, and then adding a little more variability into that to account for potential changes.
Thank you.
You're welcome.
One of the criticisms against using informative priors is that if you have a prior that is so informative, you will no longer be surprised, or it's harder to be surprised when you collect your data. And so this can make a tester feel that they might need to collect a whole lot of data in order to possibly refute their informative prior. What do you say to that?
So I think it's really important to look at the prior you're using, even if it is an informative prior, to make sure. So one thing I didn't mention is when we think about informative priors, we're really talking in relationship. I think a good way to think about it is in relationship to the amount of data you're collecting. So, beta 5.5 might be non-informative if you're collecting a lot of data, but it's very informative if you're getting 3 observations. So I think relative to the amount of data you're going to get, a really good way to go into testing is think about what is the experiment I'm going to do, and then basically do some simulation approaches to say, okay, this is the type of experiment I'm going into. If I saw this type of data, how does it change my prior, or how does it update into the posterior? And am I collecting enough data to overwhelm my prior in a way that's reasonable, or is my prior so strong that I no longer can update that, which is a very dangerous situation to be in.
So it's helpful to know the sample size you're going to collect when you're thinking about what prior you're going to form.
Very much so, yes.
Other questions? Let's give our speaker another round.